Did you find the solution? But it's what I said. You got to set it. Also, keep in mind that the frequency, the magnitude response peaks as well. And if you think of the passband for a filter, it could be whether it deviates positively or also going down as well. So, the point you can look at, is the frequency in the range where it goes up to 1 on 1.4, which is 1 on square root of 2, or whether it goes down. So keep that in mind. That it's for a filter, it's probably if it's fully damped, then it's 1 on root 2 down. But for distortion, it could be when it goes up as well. The particular RLC you have there actually has quite a peak in it. So keep that in mind. But you've got to solve, as I said, you've got to set it to either root 2 or 1 on root 2 and solve for the W, the omega. Okay. Okay. So perhaps make a start. So I think we're up to around here last time where we're looking at the PCB traces and that. Just giving some typical values before we start off on the fun stuff. Okay. So I think we had a look at this. We said that the actual properties change as a function of the trace width. Okay. For PCBs, because as you have obviously a thicker trace, then you could imagine that you have a parallel plate capacitor. So obviously the capacitance per unit length is going to increase. Okay. You can think of more little bits of capacitor in parallel, and capacitors in parallel add up. And the inductance, as you increase the printed circuit board trace width, you've got more little bits of inductance in parallel, and they decrease when you put inductance in parallel, so the inductance goes down. Okay, so anyway, we'll see later that that ratio of the L's and C's gives something called characteristic impedance, and today we'll see hopefully what that characteristic impedance means and where it comes from. Okay, so we've just had a bit of introduction. Okay, we've sort of said how we're going to make this circuit-based model. We're going to start off looking at the delta X's. Okay. So now we'll get into the real stuff. We'll start mathematical description. Okay, so as we said, the model we're going to use, we're going to be looking at, that's 440, I think got the wrong one. So we're going to be looking at this uniform line, looking at a small little bit delta X, okay, and we're going to have that delta X modeled by these lumped components of inductor and a capacitor. Okay, question is, will it, what will our model actually model for us? You could ask, will it model the actual potential difference down the line, so potential difference between this point and that point, okay? And the answer is no. What the model is actually trying to do is model this transverse potential, okay? So it's the actual task of this model is it's modeling the transverse potential difference between these two lines, okay? Now, if you have like a sinusoid or a time varying signal, okay, then it may be that it will predict, knowing that the transverse voltage at various points, you could predict some longitudinal potential difference down the line. But the actual thing that the model is trying to find is this transverse potential difference. Okay, that's the main goal of the model. Okay, and so and as I said, we're dealing with this lossless uniform transmission line, and generally it's a good starting point. Okay, so I think for most of the problems you'll encounter, you can probably use this. Okay, it's good for fairly high frequency signals on PCBs, okay, to see up to 500 megahertz, okay, in reasonable size, okay, and you can get some good results on it. Okay, so remember we're going to make the model, we're just going to model a little section like this, okay, with inductor and a capacitor. But since we have this parallel lines and it's pretty symmetric, you might wonder, well, and this looks a bit lopsided, right? So you've got all this inductance in one place and all the capacitance here. I mean, perhaps a better model might be if we split that inductor in half and put a bit on the top line, a bit on the bottom line, and we put a bit of capacitance at this side and a bit of capacitance at that side. Okay, and that may look, because the parallel lines are symmetric. Okay, so here we've got a symmetric circuit. Okay, or we could split it up in other ways. We might have inductor here and a bit of capacitance here and there, or we could split the inductor into two. Okay, and have the capacitance in the middle. So the question is which one would model more accurately. Okay, it turns out that all these models give the same results, okay? Because we're taking this delta X, tending to 0, okay? So in the limit, they'll all give the same results, okay? However, you could get in a quiz or an exam a question on how to derive equations for one of these other circuit models for the small section delta X. So it's good practice to make sure that you can derive all the equations necessary and take the limits as appropriate for all of these particular configurations. Okay, so just keep that in mind. Okay, you could get if I were to ask you to derive telegrapher's equation in an exam, I probably wouldn't ask you for the one that we did in class. I might ask you for another circuit configuration that's modeling that small section of delta X, okay? So just keep that in mind, okay? Should be able to analyze all of these, okay? Okay, let's get going. Okay, so we've got this this structure here, okay? So we've got, this is our section of transmission line, okay? And we've got our L delta X, and we've got C delta X, and we've got I of X of T, and we've got, coming out here, we've got I of X plus delta X of T, and then here we've got V of X plus delta X of T, and we've got V of X T, okay? So now we need to get some equations, looking at, relating these currents and voltage, okay? So the first one, was there's two sets of equations we can get, actually. So we could do, okay, well, we can do KCL and KBL, right? Okay. So if we were to use KBL first, what would you do? What would it be? Anyone? We're going to use KBL. How would we go? What would we do? That's right. So we go around this loop here. There's only one loop. Okay. It's around there. Okay. But, so here, that's a good point. Good point. So this diagram's not so clear. Really, remember we said that this is going to be the one model here, the inductor and then capacitor, and this is from the previous section. I think it's a little bit. I know it's a little bit confusing. Okay. I think we mentioned it. I have it here. Here. Okay. So we're just using this and this, and remember with lossless we've got these resistances that don't exist. Okay. So yeah, I know that's. I think that should be a bit clearer, to be honest. Anyway. Okay. So if we do KBL and call this delta V, okay, because that's the voltage across the inductor, okay. So then KBL going around that loop is going to be, delta V plus Vx plus delta xt minus Vt equals 0, right? Okay, something like that, okay. So we're going to have Vx plus delta xt minus Vt equals minus delta V. And delta V, okay, it's an inductor, okay, so, and in that sense, with the way we've defined delta V and we've got I t, it's going to equal L the I x t. And these are partial derivatives, right? Of course, we're just taking, I is a function of x and t, and we're just taking the derivative with respect to t. Okay, so we're going to get Vx plus delta xt minus Vxt equals, delta x there, okay, because the total L is delta x times L the I xt dt. Okay, so if we put this under this side, okay, delta x, we've got that. And if we take the limit as delta x tends to 0, okay, so we go limit delta x tends to 0, like negative sign. Okay, take limit as delta x tends to 0, that's going to be dv x of t dx equals minus L the I x t dt, right? Rightio? That's pretty straightforward. Okay, so that's one. So now we can also do KCL, okay? This was a KBL, and we can do KCL. Okay, we do KCL at this node. Okay, so we know, this is an inductor and it's a lump circuit element, so it means that coming here must also be I x of t, right? Okay, because a lump approximation, I in equals I out. And then so going down here we've got delta I, okay, delta I. So with KCL at this node here, we can see that I x t minus delta I minus I x plus delta x t equals 0. Okay, because delta I, yeah, it will be. We'll put it in a second, right? Okay. And so that's going to be I plus delta x t minus I t equals minus delta I. Okay, and delta I in this case is going to be because the current into a capacitor, for a capacitor it's I equals C dV dt, right? Okay, so this delta I, this current going into the capacitor, is going to be delta x C dV x plus delta x t dt, right? Partial derivative. Okay, so we're going to get, and again, if we take this and divide by the other side, we're going to end up with I x plus delta x t minus I t on delta x. Okay, it's going to equal minus C dV x plus delta x t dt, and we're going to take the limit as delta x tends to 0 of that, right? Okay, so then that's going to give us the I x of t dx, okay, equals minus C dV x t dt, right? Okay, so that's another equation. Okay, so it's two equations. Okay, now we can do more with those. Okay, we can start doing some more stuff with them. We could call this 1, perhaps call this 2. We can take the derivatives. Okay, again for both sides. Okay, we get some more functions. Okay, so for one, we could first do the time derivative, and remember these partial derivatives we can swap them around. Okay, their position is not important. So let's first do the time derivative for equation 1. So it'd be d squared v x t dx dt equals minus L d squared, okay? Call that 1a. And we do the same, but now with x, so we also have the v x squared equals minus L d squared I x dx dt, call that 1b, okay? And we can also go do the same for 2. So 2 would have minus c v x t. Sorry, that should be the x squared. Sorry, no, I went t first, didn't I? T squared, that's 2a. And then we've got x squared dx dt, 2b. Now, what you can do next, okay, we can try and just get an equations in I and v alone, okay? Because look, we could substitute. We could take 1a and put them 2b and put them together, okay? Or we could take 2a and 1b and put them together. So let's do that. So let's do 1b and 2a, 1b and 2a. Okay, so that means that this is going to go into here. Okay, so we're going to have so that means that we substitute that part with this. Okay, so then we're going to get d v t dx squared equals L minus L times minus c is going to be LC d squared v t squared. Okay, that's 3. And then when we put 1a and 2b, so it means we're going to put this into there. So we're going to get minus 1 on c d squared I x dx squared equals minus L t squared, and so it's going to be equal again as LC. Okay, so that's how I's and V's are related. Okay, so what does that? Have you seen equations that look like that before? Anyone? You've all done physics, so what does that equations? What do those equations remind you of? Anyone? So they're waves, right? You heard of wave equations. So these sort of equations, what they are is showing that they're waves propagating along the transmission line. Okay. So we'll look at that shortly. Okay. So we end up with this telegraph as well. That's a set, and again we can put them together and we end up with this form. Okay. 1 on UP squared, where UP is 1 on root LC. Okay. That's what we ended up with. Okay. So and just remember that in an actual transmission line, this L and C are related. We'll see that in EMT. So it's not independent. Okay. And this is the speed. This UP actually we'll see is the speed that the things propagate. Okay. So now they have solutions. So the solutions to these DEs. Okay. So this is a differential equation. These are differential equations in space and time. Okay. But for V of t to be a solution to that differential equation, it must be of this form. It must be V. Okay. It could be anything. A sign function. Okay. But it has to have the argument being t could be plus or minus x on UP. Right. So if that's that form, then that will be solutions. Okay, so the way to check that, you can check that if you want to do that yourself. We can do it. Have a quick look now. Okay, is consider. I mean, you can check it easier if you just put a sine or a cos. So if a bit more intuitive, v equals sine of t plus probably minus x on UP. If you put that into those equations, then you'd see that would solve. I mean, you do the second derivative, 2 times sine is going to give you sine back, right? Okay, but with this UP, if you're going to take the derivative with respect to x, and then sorry, here we're talking about this 2 times with respect to x, you're going to get the UP on the bottom line squared, and with respect to t, it's just going to be sine again, right? Okay, so you can see that's going to work. Okay, if in a general form, so any shape, but providing the argument to that function is t, or the form t minus x of UP, you have to look at v. It's a function of g of x and t. Okay, so where g of x and t equals t, let's say plus. And let's just take one case, right? Okay, so and then if we want to find the derivative, let's say of d of v with respect to x. Okay, what's the rule that we're going to use? If we know if v is a function of another function of x and t, what's the rule you use for derivatives that's going to give you dv dx? Anyone remember the maths? Chain rule, right? Chain rule. Okay, so that's going to equal dv dg times dg dx, right? Okay, so that's going to be equal to and we know that dg dt equals 1, but dg dx equals 1 on UP, right? In this case. Okay, so this would be is going to be equal to 1 on UP dv dx, dv dg, right? And if we do that, if we take the derivative of this whole thing again, okay, it's going to equal 1 on UP times, your V dg again times dg dx, okay, or something like that, okay? So when you take it again, you're going to get this, right? Which is going to equal 1 on UP squared, V squared dg, okay, dg squared, right? Okay, that's a function, right? So V is a function of g of x of t, okay? And g of x of t equals t plus x on UP, right?
What is
The voltage, yeah. G is just a mathematical construct, right? Okay, it doesn't have physical meaning, right? It's just something we've used to get some results, okay? So if you put that in, and similarly, if you did the second derivative with respect to time, this dg dt is 1. So you'd just get, it'd be, so dv squared dt squared equals dv squared dg squared, right? Okay, because UP, you don't have that. And so if you put those into this equation here, okay, then that'd be correct, okay? You'd get both sides being equal, right? You get 1 on UP squared dv squared dg squared on one side equals, 1 on UP squared dv, the second derivative of v with respect to g, okay? And which equal, okay? So showing that any function of v that has this form will be a solution to that wave equation, right? Okay, so physically, what does it mean? So again, probably the simplest way to check that is if you took a function like v equals sine of t plus x on UP. You know the derivative for sine, okay? It's the second order derivative. So this v of x of t equals v of t minus x of UP is a wave traveling the positive x direction with velocity UP. That's what it means, okay? So if you plotted that out and you look, so if this was a shape, v had this shape form, okay? Triangular pulse, could be anything. If you plot that at x equals 0 and it went like this, and you're looking a bit further down the line at x naught, okay, then that pulse would come to x naught a little bit later, right? Okay, so just work through that and try and get around that. So that this represents the wave traveling positive x direction, okay? Because if this is positive, then that means to get it back to 0, you need t to be increased, right? So to get to this point here, then time has to be a bit longer, okay? You need a bit of time to make this 0, okay? So with the minus sign here is a wave traveling positive x direction with velocity UP. It's the wave velocity, okay? And t plus x of UP is a wave traveling in the negative x direction, right? Okay, so just remember that. Okay, so the circuit model is linear, and we can think of superposition, okay? And complete solution to this, V, will consist of both the positive and negative waves, and possibly a constant, okay? So, any combination of a constant, the positive and the negative traveling waves, also scaled, will satisfy this equation, right? Okay. Similarly for the current, right? But these V's and I's are not all independent, okay? There's some relationship between, the V1 and the I1 and the V2 and the I2, okay? And that relationship, the derivative of V1 and I2 with respect to time, okay? And call that relationship is called Z0, characteristic impedance of line. It's given by square root of L and C, right? Okay. Now what is Z0? Okay, well, it's actually a bit hard. We'll go through quickly how to show it. Okay, derive it. It's not an easy thing to derive to find these relationships, and it's not covered in a lot of textbooks. And some places where they cover it, what they do is they look at the case where we have sine waves on the line, and they take an approach where they assume the line is lossy, but then they take the limit as the loss goes to 0, and then they eventually get to Z0. Okay, so the actual proper way to do it is to introduce some new variables. Okay, and we'll just go through that quickly now, but this won't be in the exam, right? Because it's just too difficult. But I have put these on the LMS, so you don't have to know this. I'm just putting this up to make the thing complete. Okay, so we do our KVL and all that stuff, and then we get all these things, right? So we're already done. This is on the LMS, but again, you probably need to know up to here, which I've been through. Okay, that's the fairly straightforward stuff. But to get this relationship Z0 and to see that, you need to do some transformations. Okay, so put this eta equals t minus x on UP. Okay, know that the solutions to the i's and v are consisting of these forward and backward waves. Okay, then we can get the I1 the derivative with respect to eta, is okay, and I2 with respect to neta. Okay, and find what they are, and then we know that that I1 consists of I0 plus I1. I consists of I0 plus I1 plus I2. So you can put that into there. Okay, and find. I'll put into this one here and find 4401. ELEC4401. right. Then we can put that into here, okay, and we can see that it's equal to di1 d neta times this minus 1 up, because that's what that's going to be, and then di2 d neta times d neta dx, which will be 1 up, okay, and then that's going to equal this. And then we can do something similar for v, okay, the same transformation for v, and put that into, dv dt, okay, and so that's going to equal, so this part is going to become this, okay, so it can be minus c dv1 dt eta and minus c dv2 dt neta, okay, and we can see here that, we have I1s and V1 on one side, derivative with respect to time of I1, derivative with respect to time of V1 on one side, and derivative with respect to time of I2 and derivative with respect to time of V2 on the other side, okay? And we can see that there's a relationship, so if we separate them out, you can see that for the forward and backward waves, there's a relationship between the time derivatives of I and V, and that relationship we call Z0, okay? Okay, we call that relationship Z0, okay? So it's a relationship between the time derivatives of the current and voltage of the forward and backward waves, okay? That's what it is. So, Z0, let me go back to the main presentation now. Okay, where were we here? Where are we? Let's start up again. Okay, as I said, Z0, okay? So it's this relationship between the time derivatives of the forward and backward waves, okay? So, it's not something you can measure with a multimeter, okay? You're not going to see, put a multimeter across the line, you're not going to see Z0, okay? It's something you have to infer from measurements, okay? If, because it's not relating, first of all, we'll see, it doesn't relate the total current and voltage, it's only the waves, the forward and backward waves are related, and it's the time derivatives. So if we were looking at steady state sinusoidals, then, there would be, a relationship, you could call it an impedance, okay? Because, the derivatives of the sinusoid is also another sinusoid, right? Okay. But, as I said, it doesn't equal, Z0's not equal, so, in sinusoids and also in Laplace, can be considered a real impedance, right? For time domain, it's relating the time derivatives, okay? So in the time domain, this is what it's expressing, okay? The ratio of the derivatives of the voltages and the currents for the forward and backward waves, okay? Okay, so that's what Z0 is. Any questions on that? So again, don't worry about how we derive Z0, because that's a bit tricky, okay? But the other stuff, how we got the telegraphist equations, how we found out, that there are these waves that are propagating back and forth along the line, you should be able to do that, okay? You should know what the characteristic impedance means and, how it's relating. I mean, you're going to need that, okay? When we come later to do analysis, you're going to have to know what the characteristic impedance means, okay? It's a relationship between V's and I's on, for the forward and the backward waves separately. It doesn't relate the total voltage and total current on the line, just the forward and backward waves separately. Okay. Another thing too, I forgot to mention, you'll see that for the forward wave, Z0 is positive, okay? But for the backward wave, it's negative, okay? And the reason that is when, fast, here we are. So, when we defined all these models, we had I going to the right, okay? But if we have the backward wave, we would expect, as it's flowing to the backward, that current would be going to the left, right? So, and to represent that, because of our definition, when we did derivations of how, we took current to be going to the right, it's negative, right? So you get a negative sign, okay? You go look at those equations, how we derived, when we did find Z0, you see that come out to be negative, okay? So that's another thing as well, okay? But, it's positive for the, this is Z0 is a positive relationship, gives V1 on I1, okay? It's related to minus V2 on I2, okay? For the backward wave, okay? So maybe, I think that's probably enough for you to digest today. So in next slides, we'll start looking at getting a two-port model, okay? That's what we're going to do next, okay? So maybe I'll just finish this off. Propagate. So we've got Z0. So remember we said there was two characteristics of transmission lines. There was Z0 and also the delay, okay? And, we said that, this UP is the speed of propagation, okay? So the delay is going to be basically the length divided by the speed of propagation, okay? So it's going to be, speed of propagation is 1 root LC, then it's going to be L times square root of C, right? Or Z0 times C times L. You can rearrange it however you want, okay? And typically, if the line doesn't have any special materials between it, magnetic materials, or it's not loaded with lump capacitance and inductance, then, it's typically UP is C divided by the square root of the relative permittivity of the dielectric between the lines, right? And for a printed circuit board, so the order of, it says 72 picoseconds per centimetre. So a little bit slower than the speed of light, okay, because of the dielectric. So if you had air between your conductors, then it would be the speed of light, okay? So let's stop there, okay? Any questions on that? Anyone? Yeah, all this stuff's on LMS, yeah. So it's also in the notes, I think, but I think I think I put it under resources and reading material or something, and it might be TXL equation manipulation, like that, okay? That's that stuff in green I went through where you don't have to know all of that, right? You don't have to know the stuff on Z0. It's pretty tricky, right? Okay.